All right, so today we're going to be doing lesson 1, radical review. So we're just going to be looking over some stuff that you should already know from doing radicals in grade 10. There will be a couple of little new things in here, but most of this should be pretty familiar. So obviously, first off, we know this whole thing is called a radical. But the thing under the radical, that is called the radicand. The number over here is called the index. What kind of radical we're dealing with. All right, similar to the idea of an exponent. So just remember all of your exponent laws. Those are no different than the ones you covered in 10C. Review them, make sure you're familiar with them. They run in very similar ways to the way radicals work because, as you should remember from 10C, radicals are really just rational exponents, like we can see in this law down here, where the index is the denominator of the rational exponent. So we can actually work with radicals by kind of thinking of them in similar ways to fractions. Just like you can only add and subtract fractions with common denominators, you can only add and subtract radicals with common radicands. And they are representations of real numbers, not just operations in and of themselves. They are numbers. The square root of 2 and 2, not the same number. They're different. So let's actually start working with some radicals. So we're going to start over here with the square root of 18. Now, there's a couple of ways you can approach problems like this. One way you can do it is to actually break the number down into its prime factorization. So if we were to prime factorize this guy, it would be 3 times 3 times 2. Okay? Now that we have it as 3 times 3 times 2, what we can do is we can look for pairs. Because the index of this radical, remember, if there's nothing there, there's automatically a little 2. Because the index of this radical is 2, we're basically looking for pairs that we can pull out. So I have got a pair of 3s. So in order to pull those out, nope, wrong color. When I pull those out, only 1 comes to the outside. And then the only thing that's left on the inside is the 2. I don't know why I made the radical that long. It was unnecessary. So the answer to this one was 3 root 2. Another way that we can handle it is by looking for the largest perfect square. So sometimes it's nice to just have a little list of your perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. You get it. You're probably bored of listening to me list off perfect squares. I'm just going to quickly write up a few more, just so we can use it for the remainder of this lesson. I like having the first 10 on hand. I mean, let's be real, I have the first 15 memorized, which is handy. It's nice to have that in your head. So if I look at the square root of 128, what I'm going to look for is I'm going to look for factors of 128 that are perfect squares. And I like to start from the bottom. Obviously, 100 is not a factor of 128, and 81, not a factor of 128. 64, though, that seems promising. So I start from the bottom to ensure that I'm getting the largest possible one. If I need to list more numbers to get to that largest possible one, I can do that. So I'm going to rewrite this one as the square root of, well, if I divide 128 by 64, I get 2. So 64 times 2 is 128. And 64 is a perfect square. So this is the square root of 64 times the square root of 2. And the square root of 64 is 8. So what I get is 8 root 2 as my answer. So those are the two main methods for doing this, either prime factorize and then pull out either pairs if it's a square root, groups of 3 if it's a cubed root, or else you can look for the largest perfect square factor. Now, watch out for this one. This one's not a square root. Be very careful. This one is a cubed root, so it works a little differently. So for the cubed root, we're obviously going to be working with cubes. So again, we have two choices. We can make a list of perfect cubes. That's not a big deal. I can do that pretty quickly. Or again, we can prime factorize and look for groups of 3. I'm going to do the prime factorization method, and then you can see how the list method would work exactly the same way. So note that if we're looking for the cube root of negative 64 over 27, what we're really looking for is the cube root of negative 64 over the cube root of 27. This is the same as exponent laws. You can distribute exponents over division. You can distribute radicals over division. That's okay. So the cube root of negative 64. Now a lot of you will be able to look at that and see it right away. In fact, you probably see it by looking at my list on the side here. But again, if I felt like it, I could prime factorize this instead. I could break it all down. I could say, okay, 64, that's 8 and 8. I've already kind of buried the lead, which is 4 and 2, and 4 and 2, which is 2, 2, 2, 2. So I've got all of those. So it's equal to 2 to the power of 6. I can do that as well, and I would get that this is the cube root of 2 times 2 times 2 times 2 times 2 times 2. And I could also look at the bottom there, say the cube root of 27. If I prime factorize 27, it's 3 times 3 times 3. And again, we're looking for groups of 3 now. So I've got a group of 3 here and a group of 3 here. That is a really thick pen. I'm going to reevaluate all my life choices and pick a thinner pen. Group of 3 here, group of 3 here. So I have 2 groups of 3 2s, so I'm able to pull both of those out, and there's nothing left. There's 2 times the cube root of 1 all over. I can pull out, here's one group of 3 right here, so that gives me 1 3 on the outside, and the cube root of 1 is left, which gives me to my answer of 4 over 3. Specifically, I dropped the negative along the way. That was my bad. There should have been up here. Apologies, everybody. I'm tired. It's been an interesting week. We all know this. So I still have that negative there, so this should be the cube root of negative 1 was left in there. So this becomes negative 4 over 3. We're allowed to have the negative because cube roots of negative numbers are totally fine. We absolutely can do that because negative 4 times negative 4 times negative 4 is in fact negative 64, not positive 64. And we can see that we could have also done that just by looking at our list or just by knowing our cube roots. All right. Now let's take a look at converting mixed radicals into entire radicals. So again, we need to make sure we know our index. The idea here, this one's a little bit simpler, is that in order for 3 to go and join 2 under the radical, we need to convert it to its radical form. So I can basically say that another way of writing 3 is the square root of 9. We know this works because the square root of 9 is 3. These two things have the same value, so I can write them either way and both are correct. If they have the same value, then either way is fine. And I'm going to multiply that by square root of 2. But when I multiply radicals, I can just multiply their radicands. So this is going to be the square root of 18. Hey, go figure. It's the same as what we saw in example 1. All right, next one. Now, this one, it has this negative out front. We're going to leave that because this is a square root. And we can't have a negative square root because anytime you square a negative number, it's going to come out positive. So there's no way to have the square root of a negative number, at least not in the real number set. Don't worry, you're not going to be dealing with square roots of negative numbers. For you, those aren't allowed. So I'm just going to leave the negative, and I'm going to say, okay, another way of writing 2 is the square root of 4. So what I get here is this is negative square root of 4 times 3, which is negative root 12. Do not put the negative on the inside. Leave it out there. All right, last one. Again, this is a cube root, so it's going to be a little different. So in order to do this one, we need to say, okay, if I'm going to rewrite 5 as a cube root, I need to cube 5. That just makes sense. So the cube of 5 is 125. So now that I have that, I can see that my final answer will just be the cube root of 125 times 4, which is 500. And there we go. Okie dokes. So now we've converted between radicals and mixed radicals. We've converted mixed radicals to entire radicals. So let's take a look about when variables are thrown into the equation. Well, it's an expression, not an equation. I'd kill myself. All right, so I'm so funny. So determining when a radical, I'm sorry for that joke. Actually, no, I take it back. I'm not sorry for that joke. I refuse to apologize. That was funny. It's a funny joke. Determining when a radical is defined. So for which values of the variable is each radical defined? All right. So we want to know for which values of the variable is the radical allowed to happen. So remember, square roots or even roots cannot have negatives in the denominator. Odd roots, like cubed roots, can. So the first thing I want to do with all of these is simplify them to mixed form. And just so you know, in general, we are always going to prefer our radicals to be in mixed form, because when they're in mixed form, they're most simplified. Just like we prefer our fractions in lowest terms, we prefer our radicals to be fully converted to mixed radicals. So 54x cubed. So to do this one, I'm just going to be looking for the largest perfect square factor of 54, which is 9. So I'm going to rewrite this as the square root. Remember, it's a square root. The index is 2, even though we don't see an index there. It's index of 2. So I've got the square root of 9, and 9 times 6 is 54. And then I'm going to break down that x cubed there as well. So I've got x times x times x. So now that I've got that, I know the square root of 9. That's not too bad. That's going to be 3. But I have to see how many pairs of x's I can pull out. And I can pull out exactly one pair of x's. So I've got an x out front here. And then what I'm left with under the radical is the 6 and the x. I wasn't able to pull those out. Now, again, the index is even. So since the index is even, we have to put some restrictions on this thing. There's still an x after we simplified. When we fully simplified it, there's still an x in there, so we need to consider the restrictions of that x. So x must be greater than or equal to 0. Yes, italics. I'm teaching a class right now. Go away. Sorry, my cat is wanting to be part of the lesson. I can't blame her. This is exciting stuff. She wants to learn some math. X is an element of the real numbers. So those are our restrictions. X has to be greater than or equal to 0. If we look at the cube root of 12x to the power of 5, similar idea here. We're going to be looking at the cube root, and again, I'm going to break this down, but this time I'm going to break it down, and this time I'm going to use prime factorization, just so we can see different methods. So 12, if I prime factorize that one all the way down, is 2 times 2 times 3. Italics, I'm busy. Yeah, I know, but I'm busy. And 5 x's. Sorry, in the morning she gets the zoomies, where she runs around and is really excitable. All right, so I'm looking for groups of 3. Now you'll notice in my prime factors of 12, there are no groups of 3 of the same number. So that means I can't pull anything out of the radical there. But I do have a group of 3 x's. So that means I can pull out an x. The 12, it doesn't get to go anywhere. There is no cube root factor of 12. And I'm still left with 2 x's under the radical, so I've got that there. Now, because it's a cube root, it actually doesn't matter whether the denominator is negative or positive. It's irrelevant. Also, notice that the x is squared anyway, so even if x was negative, x squared would be positive. So we can just say that x is an element of the real numbers. It doesn't matter if it's positive or negative. All right. Then we have this c here, 75a squared. So I'm going to be dealing with this one a lot the same as what we've dealt with in previous. I'm going to just break it down. So I'm going to break this one down with prime factorization again. Again, you can just use largest perfect square factor, but prime factorization is good too. So this is 5 times 3 times a times a. So I'm looking for groups of 2. So I'm going to change this pen size. It's a bit big. So I've got a pair of 5s here, and I've got a pair of a's here that I can pull out. So I got a 5 that I can pull out, and I got an a that I can pull out of there. I can take the square root of. I don't know why I made that big. All that's left then is 3. Notice there's no variables under the radical anymore, so a can be any real number. So a is an element of the real numbers. I just heard a bang. I'm assuming that my cat broke something. We'll find out later. I'm going to do one more example, just for funsies. Just for fun, do one more example. So I've got, I'm going to put in a D here, just because I can. Because you can't stop me. This is my show. I'm recording. No one else can do this. 16b cubed. I regret using 6 and b in the same thing. Let's change that to a y. All right, 16y cubed. So I'm going to be basically dealing with, again, this time I'm going to use perfect square factors. So I'm going to break this one down into the square root of 16 and the square root of y cubed. So I'm just going to show you another method for this instead of breaking down into prime factors. And I can just ask myself, okay, 16, the square root of that is just 4. So that one's easy. And y cubed, though, I can break that up into y squared and y. Y squared times y would be y cubed. And we see we've got a y squared there. I'm actually going to separate those out. Y squared and y. So the square root of y squared is just y. And I can't pull out that last square root of y. And we notice we're taking the square root, meaning that y can't be negative. It's just not allowed to be negative because we can't take the square root of a negative number in the real number set. And we're not getting into the complex plane here. So we have that y must be greater than or equal to 0 when y is a real number. And that's it. That's pretty much everything you need to know about the basics of dealing with radicals. And you can see at the bottom here, get yourself a homework assignment, get some practice to do. All right, peace.